Sound. Hello everyone. Good morning or good evening, whatever it is in your place of residence. And I'll start directly with the homework. Let's explain that real quick. We had a little Torus that we're supposed to build for NASA. NASA contracted us to build it. We're engineers, we're physicists. We have to build this thing, put people in there, 10,000 people at least. And it's going to rotate, it's going to create artificial gravity. You're going to be pushed, if you, the people who live there are going to be pushed against the rim. And that's going to be their artificial gravity. It's going to be based on Newton's second law of motion. Force equals mass times acceleration. It's not going to be based on Newton's universal law of gravitation, which is mass times mass divided by distance squared. Here, it's not a question of being close to the Earth. Here, you're spinning in space, and the only thing that's pushing you out is the force, the centrifugal force. Okay. And what was the problem that what is the problem we have to solve? Well, under the rope model, you don't have any ropes coming from the direction where the word pull is, where the red question mark is. There's no ropes coming from that side, which would be, for example, in the case of gravitation, it would be the Earth, right? So the man that's standing against the rim in this case would be standing on the Earth. He would be pulled by every atom on Earth.
To the left.
Yeah, you'd be pulling to the left, and here we have authoritative testimony. Here we have Mr. Richard Muller from Berkeley, and he says, so for example, if you have the Earth, there's a big mass here, and you have you with your little mass here. You can see the little man standing on the big mass that he drew on his blackboard. And every atom on Earth is pulling on every atom of you. You're also pulling on it. The amazing thing about gravity is that it goes right through things. Okay? So there you have good testimony. And so the question here is that, now you don't have every atom on Earth connected to you, to that little beige man there. All you have is the other equation, Newton's universal equation. That's the one you don't have. I'm sorry. You have inertial mass, which is caused by the centrifugal force caused by the rotation of the wheel. Okay? And so what is the problem with that? Well, here's Einstein's principle of equivalence that we can throw in there. And again, it seems, according to Einstein, these equations are both exactly the same. Whether you're accelerated to the Earth by your gravitational mass, you're falling at 9.8 meters per second squared because that's the specific gravity here on Earth based on the mass that the Earth has. It pulls all atoms in space, whether they belong to an elephant or to a feather or to a rock, pulls them at the same rate. Each atom it pulls at the same rate towards the center of the Earth. And on the bottom you have Newton's other equation, which is his inertial mass equation, which is a rocket just flattening you against the seat when it accelerates. Okay, so those are the things. What's the problem with this? Well, the problem with this is that when we put the threads in there and we put it in a dynamic mode, we show that there is a little bit of a difference. With a rope model, every atom of you is connected to every atom of the Earth, as Mr. Muller just finished telling you. So the only way we can conceive this is some kind of elongated entity, invisible entity that's pulling on every atom in your body. And in the case of the rope model, well, we do have the rope hypothesis, and we're saying that every atom in your body is connected to every atom on Earth through these electromagnetic ropes, which, as a bonus, it's along with it's the path along which the light travels. Conversely, on the bottom, you don't see any ropes. Why? Because ropes are irrelevant in this scenario. Here you have force equals mass times acceleration. The rocket is simply speeding because you turned on the boosters. And so this is not a question of ropes. This is a question of you being accelerated locally, in this case by boosters, right? So you're not being pulled from the direction in which the rocket is moving, like in the first case. In the first case, you are being pulled towards Earth. In the second one, you are being pushed, by your boosters. And so these are, so Einstein says these two are equivalent, and the question is whether they are. And again, you got to build the torus. You better know whether they're equivalent, because maybe there is some physical effect, whether you use Newton's gravitational law or whether you use his inertial law, right? And so let's look at these two equations. We have Newton's second law of motion, force equals mass times acceleration on the left. That's the rocket scenario. And we're going to simply assume that it's accelerating at 9.8 meters per second square. And on the right, we have Newton's law of universal gravitation. And that's the mass times mass divided by distance square. That's the key factor there. And in that case, you're falling to Earth. Why? Because you're being pulled by every atom that constitutes the Earth. One is a pull, that one, and the other one, the rocket one, that's a push. Okay, so Einstein is saying these two equations are one and the same essentially, and they use them interchangeably. In other words, whenever they want to calculate something, they are able to go in there, and I've got a little, in my website, I've got a little diagram shows what the mathematicians do. Here you have force equal mass times acceleration. They set it equal to mass times mass divided by distance squared. What is the problem? The problem is if you have force equals mass times acceleration in the first part, and the constant g times the two masses divided by distance squared in the second equation. When you put them down, when you bring them down, if you want to calculate the acceleration, for example, in Newton's second law, you just cancel the two little masses there. You leave only one mass. You take the mass on the left and you cancel it with the mass on the right, right? And you end up with acceleration equals the gravitational constant g, mass over distance squared. The acceleration is that mass times divided by distance squared. What is the problem with this? Well, the problem with this is that the acceleration, the distance embodied in acceleration, is a dynamic distance. What we're talking about here is one object moving outwards from whatever point we use as a reference, and you're essentially rolling the tape, the measuring tape, from that point to where you measure. That's not the case in the distance squared. In that distance, the distance squared is the distance between two objects, the two masses in Newton's equation. So you have a distance between two masses versus the trajectory of one mass. That's what they're comparing, and I'm saying that's an illegal motion. It should be outlawed. You can't do that because you're from a mathematical point of view, it's correct. You get the same units, no problem, and you get the same values. And in that sense, Einstein's right. The principle of equivalence, Newton's second law is equal to his gravitational law. But from a conceptual and qualitative point of view, they are not the same. One has distance between two objects. The other one is the trajectory of one object. Okay, so they're conceptually different. That's what I'm going to say is going to make a difference here. Okay, so where do we have to go with this? Well, we got to start with a definition of mass and weight. With mass, there's no problem. It's easy. We have no definition. So see, I solved that problem very easily. In fact, it says mass is both a property of a physical body and a measure of its resistance to acceleration. So they use the word in both senses. And when you look down under, in fact, this is all out of the Wikipedia, it gets even worse. It says, in physical science, listen to this, in physical science, one may distinguish conceptually between at least 7 different aspects of mass, or 7 physical notions that involve the concept of mass. So they have all these notions, these definitions. They don't have a single definition, really. It could be the quantity of matter, which is what they're referring to when they're saying it's the property of a physical object. It could be the mass that you accelerated. The more you accelerated, the more mass it has. Relativistic mass, dynamic mass. So you get all these notions. We don't know what mass is. And that's great, because when you get to weight, weight is equals to mass times the gravitational, to gravity in the local area. In this case, the little g signifies the acceleration of gravity. Like on Earth, it's 9.8 meters per second squared. So if you want to calculate the weight of whatever, you just look at the mass, right? Whatever kilograms it weighs, because we're going to weigh it. How else are you going to determine the mass? And once you get that number, you just multiply it times 9.8 meters per second squared here on Earth, and you got the weight. So see how easy it is? You're multiplying the constant g times something you don't know what it is, because it hasn't been defined. So in essence, we don't even know what weight or mass is, either one. What we do know for a fact, and that's good, thank God we know this for a fact, is that weight is location specific. Okay, and here I'm going to put the mathematical physics version of weight. And what is that? It's I'm going to have a little comparison there. If you have a box and you see all those little circular lines that are getting lighter as you go out and darker as you come in towards the Earth, well, that's the field. That's the so-called field. It gets stronger, the gravitational field, right? It gets stronger as the asteroid gets closer to the Earth, and it gets weaker as the asteroid flies away, or the comet, or the rocket.
Wait, we're saying... I'm confused. What are we talking about?
I'm saying here that I'm going to describe what weight is according to mathematical physics, and all I want to show here with these two graphs is that weight is location specific. Location is a static concept. There is no motion. That's what I'm going to make my case on. And I'm saying that that box, which is on the light field, part of the field, on that outer one, you know, the weak field part, or the weak part of the field.
The one on the left.
The one on the left. It has less weight than the one that is closer to the center of the Earth. Okay? So if I could put a scale exactly at that point, and I have no motion here, I'm just saying, look, if I take a snapshot of the first one and a snapshot of the second one, and I could weigh them at those 2 points, God's scale, right? If I could compare those weights, I would find out that the one on the right weighs more than the one on the left. Because weight is
God's scale. Can you just build a tower?
No, in fact, this is very easy. You don't even need to build a tower, because again, Mr. Newton did his job for us. He says mass times mass divided by distance squared. The distance between the box and the center of the Earth in the first case is more than the distance between the other two, than the one on the right. And the greater the distance, the lower the force, the weaker the force. So here we have the one on the left has to weigh less, because that equation is the weight equation. Essentially, weight is, according to mathematical physics, is a force. I'm going to challenge that today. Weight is a force, and it's weight that is equal to the gravitational constant, mass times mass, divided by distance squared. If the distance increases, like in the case of the left, the force is going to be weaker. It's going to be less than the one on the right, where the distance is less. Why? Because it's in the denominator. The greater the distance, right, the weaker the force. It's inversely proportional to distance. In fact, it's known as the inverse square law. Okay? So, but what I'm saying here is that, as you can see, there is no motion. We don't have to have a motion here. All we're saying is that if the box is at the weak, the one on the left, right? If it's in a weak part of the field, it's going to weigh less, according to Newton's equation. And if the box is closer to the Earth, then it's going to weigh more. What does this mean? This means that if you're in space, listen to this carefully now. You're in space, right? And you're falling to Earth. All you have to do is take one step forward. Not a big step. You can take a millimeter step. You can take an angstrom step, and your weight changes according to Newton's law. Let me repeat that. You can walk a meter, you can walk a centimeter, you can walk an angstrom. Towards the Earth, you're going to weigh more. Your weight is going to change because weight is location specific. That's the concept of a field. A field supposedly, whatever a field is, causes you to weigh more the closer you are to the center of gravity. That's what a field is. A field is just a bunch of numbers. It's a potential at each point in the region around an object. That's what a field is.
When we're talking about a field, aren't we just talking about distance? Essentially, like the one on the outermost line you have on the left and the right.
Yeah,
that's one field because
it's a weak field.
That circle essentially represents one distance away from the
correct. Exactly.
It's an aggregate of coordinates.
And it is a distance. What they've done with Newton's law to build this field, right, is they just ran it radially around the Earth. And they say, look, if we take all the distances where the darker circles are, and we take all the distances where the lighter circles are, well, then you build this field which goes from strong to weak when you go from the center of the Earth outwards, radially. Okay? So any object that's found anywhere on the field is location specific. As soon as it moves one step closer to the Earth, it weighs more. And this is important because if weight can be conceptually determined without moving anything, in other words, it's a function of distance according to Newton's law, then we got a problem because then you don't need to weigh anything. Everything has a weight, whether you feel it or not, whether you have a scale to measure it with or not. It all depends on the distance you have with respect to the Earth. Conceptually, you have a weight.
Well, more specifically, the distance you have to everything in the universe, right?
Mm-hmm.
We use Earth because that's the one that you get pulled to, because that's the one you're close to.
Correct.
It's really, your weight is also offset by all the matter pulling you that's on the other side, that's behind you, or above you, I guess you could say. To make it concrete, if all the matter in the universe above me suddenly was moved below me past the Earth, I'd probably weigh more.
Yeah, you'd weigh a lot more. That's true. So it's also location specific with respect to all the matter in the universe. The only thing is that, again, distance plays an important part there, right? Because since they're so far away, then Newton's law does have an effect. But here, yesterday I was showing you this. This is a summary of what the problem is, and with the gravitational equation versus Newton's second law of motion. And the one on the left, which is the gravitational mass, based on the gravitational equation, that's got to do with weight, whereas the one on the right has to do with velocity. And what's different here are the distances. And I'm saying that the distance on the left is not the same thing as the distance on the right. And just to summarize, so that I don't have to go through all of these, I'll just say that the first one is between two objects. It's a static distance. It's simply the separation at any given point in time. If you look at Newton's equation, all you have to do is plug in a value for the two masses and the distance, and you get only one value. And it's a static distance, okay? And that's a value you get for weight for that specific distance between two masses. That's not the case in the inertial mass, because there, the distance there is distance traveled. It's by one object, as you can see there. In the first one, you got a separation between two objects, and in the second one, you have the distance traveled by one object. So that is distance traveled, not distance. The distance of physics is the distance on the left. the separation between two objects. The distance of math is always, no matter what they do, it's always distance traveled. They're unrolling the measuring tape, they're counting tiles, they're using a timer and then divide by time and get the distance. Whatever they do, it's a dynamic distance. It's not, so it's always distance traveled, okay? That's an important qualitative difference between these, and that's what I'm going to harp on. Why? Because weight, as I said right now, requires no motion whatsoever. It only requires location of the so-called mass. Okay? So, here we have, again, you can see it in the box there that on the right, the way these people describe it, simply by location, the box has weight, has a certain weight at that location, because weight is only related to the gravitation of the object, whether it's on the moon, the Mars, the Earth, it doesn't matter. In other words, each object will have a different weight simply because it has to do with gravity. But here I have a little dynamic thing using a little GIF there, showing what's different between the rope model and what mathematical physics proposes. In this case, we're talking about physics, and we're only talking about physical objects. Every object that you see there is a physical object. It's an entity. There are no concepts in there. We have a box, we have ropes, and we have the Earth. Every atom on Earth is connected to every atom of the box. The box is falling to Earth. Okay? Here you can see that, what am I trying to show here? I'm showing that the ropes widen. The angle between the ropes as it falls gets bigger and bigger. If you compare those two angles before and after, you will see that the one on the right is wider. Okay, and you can see it there when it's falling. It gets wider. The angle opens up.
Well, I mean, if that were to fall to the center of the Earth, then it would be a 180, essentially. It would open up all the way.
Oh, yeah, by the size. But remember, then you start pulling, if you could fall to the center of the Earth and maybe go through, then you would then you would be pulled from the back, from the rear.
Yeah, that'd get weird.
I mean, if the Earth were hollow in some way, you know, it lets you pass by, or you're invisible and just go through it, then the ropes start pulling from behind you.
Yeah, you get pulled apart. I think
I guess.
It got weird.
Yeah, it gets weird. But the point here is that as the box falls, what changes is the angle of the ropes, and that's what's causing the acceleration, the 9.8 meters per second squared. That's what's causing it. That's the reason for it. There is no such thing as a field, you know, of these little circles that or shells of field that circle the Earth.
I think you skipped a step there.
I did. Oh, okay, go ahead.
It's not causing. I mean, it is causing the meters per second squared, but there's the step before that is. This shows why something that's higher up weighs less than something that's lower down, because the angle at which the atoms of the object are getting pulled is widened.
Right, correct. And that's all I'm trying to show.
But from there, the meters per second squared comes because it adds every velocity at every second.
Right.
So it's a movie aggregating all the pulls.
Right, and that's what acceleration is.
Well, not all the pulls, but it's aggregating all the speeds. I guess that's the right way of saying it.
You know, yesterday after we adjourned here, we had like a 2-hour powwow with my son. We couldn't stop. The beer stopped me after that. I don't know what he did. I went off into wild blue yonder. But one of the issues that I pointed out to him is that weight is not a force. Newton's equation is not a force. Let me put that back up there. See if I can see it here. Well, that's not the one I wanted. Where is it? No, here. I think it's this one. Okay. Weight on the right-hand side, you see gravitational mass. You see this F, this big.
That's on the left-hand side.
No, the one on the right. Let's look at gravitational mass.
Did you flip it? Oh, no, I was looking at something.
Oh, it's still not there. Okay, now it took 10 seconds to get there.
You had to flip it over in the other picture.
Okay, here we have gravitational mass on the right-hand side in blue. Okay, it's big F, that stands for force, equals to to mass times mass divided by distance squared. We're not worry about the G. We have mass times mass divided by distance squared. I'm saying that F is not an F. I'm saying that is a T for tension. And tension is not a force. And the question is, how do we justify this? Is there a reason to justify this? Well, first let's look at tension. The tension means that no one wins the tug of war, whereas force, whether you push or pull, means that someone wins it. In the case of tension, you have either compression or tension, which is the pull side of, like if you pull on a string, right? Two people pull on a string, we have tension. But if you push on your refrigerator, like we did last night, then what you have is a tension. If the refrigerator doesn't move, if it doesn't give a millimeter, an angstrom in, if it's so solid that you can't get it to move, then, in other words, you make no progress, and obviously the refrigerator is not pushing on you either, or you on the elephant's not pushing on you. Then at that point you have like a compression, but it's a tension. It's a tension. Why? Because no one wins the tug of war. As soon as something moves 1 millimeter, 1 angstrom in any direction, then you have force. But as long as there's no motion, nobody wins the tug of war, then you have tension. Now, what's the problem with this? Because when we pull on a rope or on whatever, on a string, a cable, we say, well, the string is under tension. We usually say that. That's in the macro world, right? And that's in the everyday scenario.
Everyone is taught.
Yeah, it's taught. You're pulling on a string, the other guy's pulling on a string, and we say it's under tension. Why do we say it's under tension? Because if we let go, now the string relaxes, and though even it might still be straight, it kind of relaxes and it draws in upon itself, okay? And so we say, well, it was under tension and now it's not. Okay, that's what we say. But see, we got a problem, because when you pulled it tight, okay, when each one pulled on that string and it was completely tight as it could possibly go before it rips, and nobody wins the tug of war, there is no more motion of any of the atoms or molecules in there, then we call that tension, only at that point. Tension is only a cross-section of time. Tension is location, it's a static concept. It's not motion like in force. Force requires acceleration. It requires movement in some direction. And the gravitational mass here does not, because you have mass times mass divided by distance squared. All you have is distance, a separation. There is no motion in Newton's gravitational equation. If you replace gravitational mass with the word weight, or the letter F with the word weight, that's exactly how weight is calculated. Weight is location specific. Mass times mass divided by distance squared. Only distance between the masses. That distance there is separation, not dynamic distance, not distance traveled. They turned it into distance traveled because they have to measure and say, well, how many meters do we have between the two tables? But that's a separate issue. That's for calculation. Conceptually, that distance is simply separation. Whether you measure it or not, Mother Nature doesn't care. She says, look, you're going to have a certain weight at a given distance, period. Then weight is equal to that equation, and if that's the case, then that's a tension, because there is no motion in weight.
What does it matter if it's a tension or a force?
It does matter, and I'm going to show that right now. That's good. You came with the question at the right time. Here we have an elephant on the left-hand side, and he's weighing the scale, right? And now we have another elephant on the right, and we're going to drop that elephant from who knows where, and he's going to hit the scale. Well, as you can see, the scales, the one on the left weighs less than the one on the right, even though these two guys are twins. They weigh exactly the same. They have the same mass. They're made out of the same atoms, but they don't weigh the same, right? They're supposed to weigh the same, but they don't. And you say, well, how can that possibly be? I mean, right now, the two elephants are just sitting, cross-section of time, right? They're just sitting on the scale. And at that point in time, when you took the snapshot, one guy weighs twice as much as the other guy, for example, right? And you say, how can that possibly be if weight is location specific? We have location, right? We are not taking into consideration momentarily the fact that the elephant on the right was dropped. So they should both weigh the same if weight is attention and tension is location specific. That's the Earth, by the way, in dark on the bottom. So they're both at the same distance, more or less, from the center of the Earth. They should weigh the same, you know, in both cases. But it turns out that we got a little detail here that the one on the right was dropped. So the issue is the following. When the elephant is falling, you have to add Newton's second, because that's acceleration that he's got there. That's got nothing to do with gravity. You know, you're throwing the elephant from an airplane, right, or whatever. So he, you know, and you're pushing him down. So he's coming already with a certain speed. Okay, it's dynamic. So you would have to add that force with which he's coming, which is Newton's second equation, second law, to the gravitational mass of the elephant that's sitting on the scale. So that's why, you know, when the elephant is moving, it's not the same thing as when the elephant's just standing on the scale. If he's falling on the scale, he's going to weigh more. In fact, you can do this at home. You can stand on the scale and you will note that at that point you weigh, I don't know, 70, 80 kilograms, whatever. That's what you weigh when you're standing completely still and you just take a reading. Now you jump, and obviously you're going to see that thing go whang, you know, the meter's going to go high. And you say, hey, I weigh more now. I weigh 100 kilos now. You did, but because you have to add the force caused on the scale by Newton's second law applied to you. You're falling. So right now you're not talking about anymore about just gravitational acceleration. Now you have to add Newton's acceleration, which is a dynamic distance. You fell a certain distance. It's not the same distance as in the bottom case, the red one, the distance squared, that's separation. Okay? So again, this again shows that, once more confirms that weight is location specific. Weight, I argue, is attention. You cannot confuse it for a force because no one wins the tug of wars, the war. You have only distance between two objects, right? That's Newton's equation right there. And so weight is attention, and weight is not a force. Whatever they do for calculations in math, and you can say, yeah, it's the same number and it's the same units, perfect. But from a conceptual and from a qualitative point of view, they're not the same. Okay, so weight is not a force. Weight is attention.
What I like about the rope hypothesis in regards to gravity and distance to the center of the Earth is conceptually you can count the ropes attached to an object and their actual what do you call it? Angles from each other. That's so what I. You can actually give it a static weight at any moment, at any distance. So if you have a perfect ball, like a baseball, and it's 100 meters from the ground as opposed to 1,000 meters from the ground, you can basically just note the difference in angles, essentially aggregate the difference in angles, fanning out, getting wider, to see what the difference in weight is. It's static at all times. You can just count the angles.
Yeah, one of the things we talked about yesterday, and that's the one I wanted to mention, then I got sidetracked there, but one of the things I wanted to mention is that yesterday when we talked, I said, you know, under the rope model, you can quantify weight without measuring anything. You don't have to. You don't have to put a scale. You know, the elephant's falling. He's still falling down the earth, and you say, well, how am I going to put a scale under the poor elephant? You know, I mean, He's falling. I can't stop him. I can't put the scale right at a given point, stop the clock, stop the world, stop the universe, and say, okay, what does he weigh at this point? So you say, well, you gotta conceptualize it. And then you have trouble conceptualizing it. You say, well, how do you conceptualize weight if you don't have a scale to measure it with?
You push the scale against its feet.
Yeah. But what is the issue? The issue, as my son just said, and let me just reinforce that or clarify it or whatever if it wasn't clear. The number of ropes converging upon every atom of the elephant at a given distance. If we count the number of ropes, gazillion, 1 trillion, 1 trillion and one, whatever the number of ropes are, from the earth connected to him at that point, that's the weight of the elephant. At that point.
Effective ropes. You're not counting ropes, you're counting angle differences.
Effective ropes. Remember, there are atoms, mass behind atoms.
You know, get more ropes on the way down.
My son doesn't let me get away with anything anymore. I created a monster. Anyways, you got atoms behind atoms. You know, even in a diagonal manner, the Chinese are behind us. Let's put it in a different context. What is it? North America is above South America, right, on the globe. If you're falling in the direction of the North Pole down to the South Pole, well, you'll hit North America before you hit South America. Well, North America is blocking a lot of atoms through the Earth of South America. They're all, in the same line.
Does that mean they're basically pulling along the same rope?
Yeah, they're all
guys behind me.
They're all lined up.
It's kind of like a tug of war where the guy in the front is pulling harder than the guys behind him.
He's the only guy pulling.
Well, no, they're all pulling.
The other guy's just holding the rope.
The other guys are essentially pulling against him.
Yeah.
If they're pulling at all.
Right, if they're pulling at all. But again, the only way you can pull is when the atoms start separating. And they separate with just a decrease in distance. As the elephant falls to earth, the ropes open up, and we're going to call those effective ropes. That means now when they act individually upon the elephant, upon the atoms of the elephant, now we're going to call them effective ropes, no longer just ropes.
To make it mathematical,
yeah,
we're really just talking about degrees of angle. The angle, you get more average degree, angle width.
The only problem with that is that, remember, it's if you have a ball or something which is uniform, completely uniform in its structure as well as in its shape, like a ball of iron, completely, like if it was a perfect ball, an ideal ball, then you could do that. But when you have an elephant or you have a feather or a rock, no, because now you have every atom, right? Yeah. And this atom has this angle, this one has this angle. They all have a kind of like a little different angle with respect to the Earth.
The average.
Okay, the average, you could say,
yeah. Goes up no matter what.
You could do the average of all those. That's good. And the other one
goes up,
or you can just count if
because
you
the further away that if that thing was on the moon, you have almost a 0 degree angle. Like you talk about
the linear region.
Yeah, coaxial?
Yeah,
that would be essentially the average would be almost 0 because they're all so far away. It's a straight line. While the closer and closer you get, even an angstrom, the average goes up by a fraction. Fraction.
Here we have Shamus, and he says, angles of the fanny ropes.
We get the angles going up.
We have the fanning ropes,
but
fanny ropes.
I don't like talking about number of ropes or number of effective ropes. That's also confusing. I think it's more...
Why is that confusing? No, hold it. Why is that?
It's more accurate to talk about the angle of the ropes. Because that's all that's changing.
Well, the angle is changing, obviously. That is one way.
But I think that's clearer.
Well, okay, that is clear. That is clear. But you have to also correct. But you also have to be able to visualize what's happening physically. Okay, and yeah, it's a mess because you say, what am I going to do? Count all the ropes or the effective rope? No, but you have to consider
effective ropes. See, because we're not only talking about ropes behind ropes. If you have a wider angle, they're both effective ropes. They're just more effective now.
Right, okay, more effective rope. See? But all I'm saying is from a conceptual point of view, what's happening, if you're trying to visualize this, is every atom, like Muller said here, right? Professor Muller, Berkeley, we can't challenge him. He's an authority, right? So he says that every atom on Earth is pulling on you. And that's exactly what the ropes do. Every atom pulls on you, and that means you got gazillions of ropes, no matter what's out there, an astronaut, an elephant, a feather, it doesn't matter. You got gazillions of rope converging upon this object. And yeah, from a conceptual point of view, you would have to count the number of ropes at a given distance, or the angle, as he says. And then you can say, look, I know the weight of this thing. I'm not going to give it to you in kilograms. I'm not going to give it to you in terms of acceleration.
I can give it to you in degrees.
I'm going to say it's at 45 degrees, or I'm going to say it's got 1,000,000,003 ropes.
Effective ropes.
Effective ropes converging upon it. Whichever one you like. Whichever one suits you better.
Yeah, I don't like it.
He doesn't like. My son doesn't like. Too many ropes for him to count.
Yeah,
So
no,
he's lazy. He doesn't.
You still have to count the angles anyway.
Yeah, but the angle is counting is a little better than counting a gazillion ropes.
Yeah, you have a gazillion angles.
Yeah, but you're going to take the average. Oh, yeah. I mean, you have to calculate. Yeah, in a sense.
But effective ropes makes it confusing. It sounds like you're adding or subtracting ropes when the ropes always.
Yeah, no. You got to clarify the concept.
It's always a billion ropes, but the average of the angles goes up.
Yeah. So either way you want to visualize it, that's my proposal. I'm saying there is no gravitational field around the planet.
Basically, it goes up until the angle is 360. Until you're in the center of the Earth.
And then they pull from the side. That's when you stop, when the center of the Earth.
That's when the average is 360.
The buck stops there.
That's the highest it gets. You can't get closer to the center of the Earth than the center of the Earth.
So, okay, that's my proposal, and that's what I'm challenging mathematical physics with. I'm saying first, let me recap. I'm saying that Newton's equation is not, gravitational equation, is not equal to Newton's second law. Okay, force equals mass times acceleration. These two guys are not the same. Einstein said it's the same. Why? Because the numbers that you get are the same and the units you get are the same. Mathematically, they're the same, so they're the same, right? Yes, but not physically. So math is math and physics is physics. Never the twain shall meet. Qualitatively, conceptually, they're different.
Well, not never. You were using math too just now.
Yeah.
Cheating.
Just to make a point here. And the other one is, weight is Newton's gravitational equation. But what does the establishment say? What do you learn in school? Well, they say that weight is a force. You look it up, you'll see that weight is a force. And why is it a force? Well, there's like two kinds of weights, at least general kinds of weights. One is when you squeeze the scale down, right? And you press on the springs or whatever your scale is made out of. And that's one type of weight. The other one is the one used maybe by the people at NASA, the engineers, the physicists out there. They call themselves physicists, the mathematicians, and that's a potential at each point in space. And that's Newton's equation. Newton's equation is not the one where you step on the scale, even though it is in this sense. And I was telling my son this yesterday. You say, well, when I stand on the scale, I'm pushing the scale down. So there's motion, right? Yes and no. When you're measuring, I-N-G. When you're measuring, there's motion. But when you finally take the final reading, that's a cross-section of time. That's only a single reading. That's when the scale supposedly stopped, right? Let's conceptually, right? It stopped. There's no more motion. And now you take the tension that you have in that situation. So again, weight is a tension because you have to wait for the scale to stabilize. Again, you can jump on a scale. In fact, every time you go on top of the scale, usually it goes back and forth a little while until it stops. Well, conceptually, you have to wait. You can't do this maybe in the bathroom, but from a conceptual point of view, you have to wait completely until all motion in the universe stops before you take a reading. At that point, it's a cross-section of time. That's where you take a weight, reading of weight.
In kilograms
so measuring is not the final reading. Those two things are different. So you say the scale always moves. Yeah, but you got to wait till it stops. And when you take that reading, conceptually, you've taken a reading at a cross-section of time. That was your weight at that point in time.
Essentially a balance, or balance. The needle is basically the relay of how much you're pushing on it. the top of the weight relays the force into the needle going away from the zero. So it's basically a relay of force.
Yeah, because that is force. It is Newton's second law in that sense that you are creating you're creating a push, right? You're creating a force. That is a force, and that is Newton's second law. But what I'm saying is, if you were to calculate the mass times mass divided by distance squared that you're measuring with a scale, what you're measuring is the attraction of the Earth on you through the scale. The scale is pushing upwards and you're pushing downwards. You're trying to get to the center of the Earth. The scale won't let you. That is Newton's Newton's gravitational equation. That's mass times mass. That's just distance between two masses, you and the center of the Earth, essentially. And so if you look at the equation, it's static. There's no motion. There's no acceleration in Newton's universal law. It's a tension, and weight is a tension. It's a static concept, not a dynamic concept. And that's one of the problems I have with what they say, because I can't remember now which one of these has it. But one of these I won't look for it. Has weight. Oh, it's in the definition of weight. That's where it's at. Hold it. Let me get that so I can talk intelligently here. Where is it? Definition of mass and weight. Here it is. Look at the bottom one. Weight is supposedly equal to mass times the gravity in your region. That's the gravitational acceleration, that little g. It's not the gravitational constant g, which is a big G. This is a little g. That's the acceleration in your region. If you're on the moon, that g is going to change. But here on Earth, pretty much near the surface, it's 9.8 meters per second squared. Okay.
How did they get that little g?
Oh, they calculated that. They calculated the g on Earth.
But how? I mean, like, how did they get the difference in the moon? Like,
by the mass of the moon. They first calculated the mass of the moon, and based on the mass, they already knew before they sent the astronauts or rockets out there. They already knew, they already calculated what the gravity on the moon is. Based on its mass. First they calculated the mass of the Earth. In other words, the weight of the Earth, the weight of the sun.
The weight of the Earth.
The weight of the Earth based on you can calculate that, because all you have to know is first the gravity.
You put the balance on its head.
No balance. It's all calculation.
You put the balance on its head, and the spindle goes around and around.
That's why the mathematicians like to say, let me push this a little bit aside here. That's why the mathematicians like to say, look, we've got the language that, can tell us everything. No, they can tell you, how much the Earth weighs. They can do that. And that's not a problem. But that's not science. So what? So what if it weighs? What have you explained with that? You haven't explained anything.
They can get descriptions and derivative. They can get descriptions and derivative descriptions from those descriptions.
Right. You get more descriptions. That's it. All you're telling me is how much the elephant weighed. You haven't told me anything about what the elephant did, if it was naughty or nice or anything.
So how much does the Earth weigh?
What is it? 2.4. I can't remember. 24 times 10 to the minus 24 to the 24th kilogram, something like that.
Weight of the Earth. Whoa, that's a big number.
What is it?
5.972
times 10 to the 24th.
Yeah.
Yeah, it's in the 10 to the 23rd, 10 to the 24th range. Anyways, the kilograms, right?
Yeah.
Yeah. So we know how much the Earth weighs. Is that science? Well, that's a calculation.
That's a fun fact.
Yeah, it's a fact. It's a fun fact. That's it. And that's also in relation to the kilogram, which we invented. Mother Nature didn't invent the kilogram.
We got to give it some unit, some tile to.
Yeah, so that's a separate issue. What I'm saying here, we got weight, right? And weight is mass times the acceleration of gravity here on Earth. Okay, and and that's at. You can put 9.8 at surface level, but as you go farther out, you got to put a different number there. Remember, you're farther away, your gravitational acceleration is a little different in different areas. You got to change in this number. So what's the issue? The issue is that acceleration is misleading, because acceleration is not weight, weight is not acceleration. What they did here, they did that little trick that I showed earlier, where they put, you know, Newton's equation on one side and Newton's universal gravity equation on one side and Newton's force equation, the second law, on the other side, and they make them equal to each other. And then they calculate acceleration. They say, oh, accelerations look equal to all of this. But the distance on the right-hand side of that equation is a static distance separation, whereas the acceleration is a dynamic distance of one object, how much it moved from a starting point. And that's the one they're using here. And that's why this is misleading. This is correct mathematically. It's not correct physically, qualitatively, conceptually. Okay, that's all I'm saying. And so weight is attention. And when you see this little g there, I'm saying that's misleading. And that's my argument. You don't have to believe me. You just hear my side of the story. Okay, that's all I'm saying here. And that's it. That's all I have today. Again, what I want to make sure is that we all understand that if you're going to build a torus, which is where we started this, you got to find out whether the principle of equivalence makes any difference out there in space, right? Because if you build a torus and it turns out that there is a physical difference, right? The influence of the earth on every atom in your body, pulling by ropes, right? Every atom of your body is tugged or connected to every atom on earth. Now you don't have that situation out there in space. Now you're in the torus, and you have a totally different scenario, which is now you bring in Newton's second law and say, look, I'm going to twirl you around and I'm going to cause the same gravity, right, that you had on Earth. Well, yeah, but see, on Earth I was being pulled and here I'm being pushed. So qualitatively it's not the same, and if we introduce the ropes, for sure it's not physically the same.
I think they're aware of that.
Yeah, and well, they know it's not the same, but they say, what the hell? You know, maybe it makes no difference, yeah. But maybe it does make a difference. And one of the questions that pops up on this is one that we started yesterday. I still don't have a complete answer. I'm not satisfied with what I did. Some research today. I didn't have time to research it completely. I'm going to continue tomorrow on that. But it's the issue of, you know, if you have a bird or a fly inside an airplane. In this case, we're going to put the fly out there in middle of space, or the bird. Maybe it's better a bird because it's a little bigger and, you know, you kind of have a better idea.
In the middle of space?
Yeah, no. Hopefully in the middle of the torus. But this is my issue. And listen to this. This is my argument, okay? I'm saying here you have a bird inside an airplane, okay? You have an eagle, big one, okay? Condor, better? Okay, I'll put a condor. Condor or eagle. You got it in the airplane. The airplane accelerates. Okay? Does the eagle get squashed in the back of a room?
Yes.
Well, when it accelerates at the beginning, yes. Once it's going at a constant speed, no. Why? Because the bird is flying within the air contained within the airplane.
I want to see that experiment. Just shuttle goes off, bird slams against the back.
No. There's a real good one that I saw today, and that's, you know, if you want to go to the bathroom, you're in the front seat of the airplane, number one, and the bathroom's in the back of the plane near the tail. Well, it's very easy. You just jump, take a step high, and the airplane goes by and you're there. 2 seconds or 1 second, right? Is that the way it works? You're in the first seat, right? You stand up and you say, I don't want to walk all the way down there. I'll just jump. And jump, you let the airplane go by, and you're in the seat of the toilet, right? Isn't that the way it works? No, it doesn't. For some reason, when you jump, you come back to the same spot you were. You say, how can that possibly be? I mean, what's pulling it? What's in the airplane pulling on me together?
I had a friend who couldn't understand that. We tried explaining it to her, and she just, like we did it with the train, where when you jump on a moving train, why do you fall back in the same spot? Right. She just couldn't understand it no matter how we explained it.
Yeah, it turns out you're traveling at the same speed as the airplane, and so your horizontal motion has nothing to do with your vertical motion. So if you jump up and down, you're still moving at the same speed as the airplane.
You're jumping in a curve.
Right.
You're not jumping straight up.
Right. No, but someone introduced another factor which is very important too, and you got to keep it in mind when you're doing conceptual things of this nature, and that's that the Earth also, you know, rotates and at a certain speed, So whether the airplane is going together with the Earth or not, there's going to be a change. But let's assume both the Earth and the airplane are traveling in the same direction. Okay? So here you are. You're going in the same direction as the Earth. The Earth is twirling. You are going in the same direction. And you have to factor, the airplane is also in the air that's enveloping the Earth. So what this guy is saying, and besides, every atom of the Earth is, according to the rope model at least, is connected to every atom on Earth as well. So, this thing is going like this. So the airplane is also, it can't do what it wants. The Earth is also taking it with it. So you got to factor that speed, the speed of the Earth as well, together with the motion of the airplane. If the Earth were to stop and the airplane were to continue, we probably would notice a little bit of a difference. So they're both moving, and you can have the same situation inside the airplane. Not only are you moving as fast as the airplane, but you're moving as fast as the Earth is rotating.
Well, what's that have to do with the eagle?
Okay, now, so no, I just want you to consider all these things. There's a lot of stuff to look at here, okay? But now you have the eagle, right? And you have the eagle and you let him go inside the airplane. When it accelerates, yeah, the eagle gets thrown back. But once it's at a constant speed, the eagle can fly around and just because it jumps, like because you jump, you don't go in the back of the airplane. In the same way, the eagle can go anywhere it wants because the air inside of the airplane essentially is taking him with him. One, he's only flapping in the air that's inside the airplane in the immediacy of his wings. And the other one is that, he's traveling at the same speed as the airplane, whether he knows it or not. He's got a free ride. But where's the problem? Or that I see, or something else that you got to factor in. Let's just say that. Let's not call it a problem, but something you got to factor in. Every atom of the eagle is tied to every atom on Earth, being tugged by every atom on Earth. So there is an inertia built into anything on Earth, whether you travel in a car or an airplane. That inertia comes from the fact that you are also connected to every atom on Earth.
What do you mean by inertia?
Well, why did you fall to the back of the airplane when the airplane accelerated? I mean, why didn't you just float?
Because the airplane moved.
Well, the airplane moved, but you're also tied to every atom on Earth. So that's where the inertia comes from your own weight.
No.
There is a weight there. Yeah, you're tied to every atom on Earth.
Inertia has nothing to do with gravity. On the ISS, if the rocket boosters go forward in a vacuum, assuming, they'd also slam against the wall. Okay, ISS is also within gravity, but if you're in the middle of space, and you're in the center of a vacuum, let's say, just to take out air out of it, and you're just standing in the middle of this sphere ship, and the ship started moving forward, you'd also fall back. It has nothing to do with gravity.
You'd fall back. Why would you fall back?
Because the rocket moves.
Acceleration.
Because the rocket moves and you don't. Not yet, until you hit the wall and then you're moving.
Yeah, but again, the question is whether you move floating back or gravitational back. Are you
just crash?
Well, hold it. No. But what I'm saying is, are you you're on the floor, right? Well, you're kind of. This is the issue. The issue when you're out in space, and that's the point really I wanted to make with all this. If you're floating in space, like because there's no gravity. And if the rocket accelerates, you get pushed to the back. Yeah, but what I'm saying is there a difference? This is the only thing the point that I'm trying to make. When you're on Earth, the eagle, whoever's on the airplane, is also tied to every atom on Earth. That's not the case when the eagle is out there in the Torus. There is no inertia in that sense. All we have is just the motion. Newton's second law. That's all we have. Acceleration. We don't have gravitation. And so the question is there a difference on the eagle from a physical point of view? There is a qualitative difference, but does that cause any physical problem or difference? Whether the Torus spins and the eagle's just flying there or whatever because it's used to that. But at the same time, the eagle's not connected to anything, so it doesn't have that earthly inertia, that tug from the Earth. And the question is, that makes a difference inside the Torus? That's my question.
I'd say it wouldn't.
but you got to justify it. I mean, we don't have a torus to run the experiment and observe whether that makes any difference or not. You know, we can only deal with this conceptually.
Well, I saw today the zero gravity videos.
Yeah, we did a lot of research with my son on zero gravity
with flames.
Oh yeah, I saw the flame there. I didn't see it, but what did it show?
When there's less gravity, the flame doesn't go up as much.
When there's less gravity.
Well,
wait, yeah,
not gravity. It's not really gravity because it's always the same gravity.
So what was it?
But it's when there's less what do you call that?
Acceleration, mass, what?
When it's in free fall. When it's
free fall
versus
you don't feel the gravity.
Yeah,
right?
I forget what you feel. The candle.
Oh, okay. So you fall with the candle.
Yeah, you got a candle.
And your
airplane's going normal.
It's not going to help you.
When the airplane does a nosedive, for example, and you're in free fall, the candle, the shape of the flame gets less pointed. It gets kind of more ball-like.
When you're so when you're falling with a candle,
yeah,
you start out with a very sharp, pointy flame, and now it's going to round. Okay, now it's going to get long
too.
Okay, long, and now it's going to get flattened and rounded out.
Yeah.
When you have free fall, in free fall.
Yeah.
So you're falling off an airplane. Let's see if I get this right. You're falling off an airplane with a candle. Not much help, right?
No, you're not out of the airplane. You're still in the airplane.
So the airplane. So the airplane is falling.
If you jump out of the airplane, the candle will go out.
Okay, but are you saying the airplane is falling?
Yes. Well, I mean, they do it with zero G maneuver, with that weird angle.
Oh, okay.
Everything in there is.
So we have zero gravity, that 20-second curve, right?
Yeah. I don't like calling it zero gravity. In normal speech, it's called zero gravity. You still have gravity, but you're falling essentially. And so you still have weight.
Okay, and it's nice to know what the effect is. Has anybody an explanation for that?
Yeah, they're saying, for example, the opposite is also true. If while the plane is going up, they have 1.8 G's, almost twice the effect of gravity.
Okay.
And the candle gets more pointed. It gets longer.
It does.
Not by much, but it gets a little longer and more pointy.
Here I have, let's see if I can get this up here. Yeah, there we go. Here's a more or less what we're talking about here. This is how they create that zero gravity. The airplane travels at a 50-degree angle, rises at a 50-degree angle against the gravity of the Earth. And only in that spot, 20-second spot from 20 to 40 seconds, that duration there, that's the only time that you get that zero gravity and you start floating in space. And by the way, these flights, if you ever want to take them, they cost $7,000 a pop. So if you want to ever know what zero gravity feels like, or microgravity, because it doesn't really go to zero.
Normal, this is on the ISS.
Oh, I see. Okay.
Because the
that flat. Too bad we can't show it here, but yeah, it's quite flattened out, quite rounded.
A ball
and it's also blue.
There's no direction.
One is blue and the other one is yellow.
Because there's it doesn't know which direction is up, essentially speaking. Here, the air is going, the cold air is going down, and the hot air is going.
Okay, maybe I can show that tomorrow. Okay, he's got it in his computer there. But anyways, here, this is how they create that zero gravity. That means you don't weigh anything in that curve, in the curvy part of the curve, right? Which is that concave in the middle. And yeah, they cost like $7,000. You float in air there. You're floating inside the airplane. But the issue here is that, what is weight at that point in time? And they say, well, you really weigh something, because you do weigh conceptually. It's just that your weight right there is offset by what the airplane is doing. So what the airplane is doing is essentially canceling out the gravitational pull on you at that point. That's why you're floating. Do you weigh? From a conceptual point of view, you still weigh. Why do you weigh? Because weight is a potential at each point in space. In other words,
it's the aggregate angle of all the ropes.
You have, if you got ropes connected to every atom in your body, to every atom on Earth, and you're on that airplane, you have so many ropes connected to you. We'll call them a trillion, or you can have the angles, as Adrian said here a minute ago. You have a 45-degree angle, whatever it is, and either way, you have weight from a conceptual point of view, because again, we don't have to measure weight. We can conceptualize weight, and at that point, whatever cross section of time you take, you have so many ropes connected to you. That's your weight, and that's the way you present weight in physics. Now, the way they do it in math, they do it, with kilograms and other stuff that they never defined. So
I had one more weird scenario for the torus.
We got a last one here. Yeah.
If the torus is small enough, right, we'll make it a cage, like the biker in a cage.
Okay, biker in a cage. It's small.
The cage is, let's just say it's only a meter, 3 meters. Let's make it 3 meters. Wide, in diameter.
Which is about a little more, maybe 10 yards. You got 10 yards.
That thing was spinning. You have a spinning cage, really fast. Right?
Okay, the cage is now spinning.
Yeah, the cage is spinning.
And the guy's motorcycling inside it?
No motorcycle. It's just a person. Okay. Two people. And they're at 180 degrees from each other.
Okay, they're in the cage.
They're head to head, essentially. Top of the head touching top of the head. So far, so good?
Head to head?
Yeah.
So they're standing.
The cage is spinning.
The cage is spinning. They have their feet against the walls.
Yeah.
And they're head to head. Okay, now what happens?
If one guy hands another guy a spoon, what direction does the spoon go? He just has to pass the center of the spin, and then it goes that way?
Okay, we'll take that. I need a beer to answer that one. Okay. Tomorrow we'll continue and wrap up mass. Again, it'd be nice to know what you think. Whether if you're on the torus, if it makes a difference whether you use gravitational mass or inertial mass, because all you're going to have in a torus is inertial mass. Will that affect you differently than here on Earth where you have gravitational mass? That's still the homework. You get one more day to figure it out, and maybe one of you comes up with a good scenario to illustrate what would happen in one case and the other. We'll see you tomorrow. Bye-bye.